The junction gate field effect transistor is the simplest type of field effect transistor. They are three-terminal semiconductor devices that can be used as electronically controlled switches, amplifiers, or voltage-controlled resistors. Unlike bipolar transistors, JFETs are exclusively voltage-controlled in that they do not need a biasing current. Electric charge flows through a semiconducting channel between source and drain terminals. By applying a reverse bias voltage to a gate terminal, the channel is pinched, so that the electric current is impeded or switched off completely. A JFET is usually on when there is no potential difference between its gate and source terminals. If a potential difference of the proper polarity is applied between its gate and source terminals, the JFET will be more resistive to current flow, which means less current would flow in the channel between the source and drain terminals. Thus, JFETs are sometimes referred to as depletion-mode devices. JFETs can have an N-type or P-type channel. In the N-type, if the voltage applied to the gate is less than that applied to the source, the current will be reduced. A JFET has a large input impedance, which means that it has a negligible effect on external components or circuits connected to its gate. Structure. The JFET is a long channel of semiconductor material, doped to contain an abundance of positive charge carriers or holes, or of negative carriers or electrons. Ohmic contacts at each end form the source and drain. A p-n junction is formed on one or both sides of the channel, or surrounding it, using a region with doping opposite to that of the channel, and biased using an ohmic gate contact. Function. JFET operation is like that of a garden hose. The flow of water through a hose can be controlled by squeezing it to reduce the cross-section. The flow of electric charge through a JFET is controlled by constricting the current-carrying channel. The current also depends on the electric field between source and drain. Construction of the conducting channel is accomplished using the field effect. A voltage between the gate and source is applied to reverse bias the gate-source p-n junction, thereby widening the depletion layer of this junction, encroaching upon the conducting channel and restricting its cross-sectional area. The depletion layer is so called because it is depleted of mobile carriers and so is electrically non-conducting for practical purposes. When the depletion layer spans the width of the conduction channel, pinch-off is achieved and drain-to-source conduction stops. Pinch-off occurs at a particular reverse bias of the gate-source junction. The pinch-off voltage varies considerably, even among devices of the same type. For example, VGS, off, for the TEMIC J202 device varies from a 0.8 V to a 4 V. Typical values vary from a 0.3 V to a 10 V. To switch off an N-channel device requires a negative gate-source voltage. Conversely, to switch off a P-channel device requires positive VGS. In normal operation, the electric field developed by the gate blocks source drain conduction to some extent. Some JFET devices are symmetrical with respect to the source and drain. Schematic symbols. The JFET gate is sometimes drawn in the middle of the channel. This symmetry suggests that drain and source are interchangeable, so the symbol should be used only for those JFETs where they are indeed interchangeable. Officially, the style of the symbol should show the component inside a circle. This is true in both the US and Europe. The symbol is usually drawn without the circle when drawing schematics of integrated circuits. More recently, the symbol is often drawn without a circle even for discrete devices. In every case the arrowhead showed the polarity of the p-n junction formed between the channel and gate. As with an ordinary diode, the arrow points from P to N, the direction of conventional current when forward biased. An English mnemonic is that the arrow of an N-channel device points in. Comparison with other transistors, at room temperature, JFET gate current is comparable to that of a MOSFET, but much less than the base current of a bipolar junction transistor. The JFET has higher transconductance than the MOSFET, as well as lower flicker noise, and is therefore used in some low noise, high input impedance op-amps. History of the JFET. The JFET was predicted by Julius Lilienfeld in 1925, and by the mid-1930s its theory of operation was sufficiently well known to justify a patent. However, it was not possible for many years to make doped crystals with enough precision to show the effect. In 1947, researchers John Bardeen, Walter Hauser-Brattain, and William Shockley were trying to make a JFET when they discovered the point-contact transistor. The first practical JFETs were made many years later, in spite of their conception long before the junction transistor. To some extent it can be treated as a hybrid of a MOSFET and a BJT, though an IGBT resembles more of the hybrid features. Mathematical model: the current in NJFET due to a small voltage VDS is given by treating the channel as a rectangular bar of material of electrical conductivity, where ID equals drain source current, B equals channel thickness for a given gate voltage, W equals channel width, L equals channel length, Q equals electron charge equals 1.6 x 10^19 C, I 1/4 N equals electron mobility, ND equals N-type doping concentration. The drain current in the saturation region is often approximated in terms of gate bias as, where IDSS is the saturation current at 0 gate source voltage. In the saturation region, the JFET drain current is most significantly affected by the gate source voltage and barely affected by the drain source voltage. If the channel doping is uniform, such that the depletion region thickness will grow in proportion to the square root of the gate source voltage, then the channel thickness B can be expressed in terms of the zero bias channel thickness as, where Vp is the pinch-off voltage, the gate source voltage at which the channel thickness goes to zero, A is the channel thickness at 0 gate source voltage. Then the drain current in the linear ohmic region can be expressed as, or see also constant current diode. References: external links, Physics 111 Laboratory, JFET Circuits IPDF, Interactive Explanation of N-Channel JFET.